Hello, in this video I'm going to show how to solve this problem involving these two carts which are connected together by a rope. So the assumptions we're making in this problem is that the rope is massless, that the wheels on the cart and the pulley that the rope is going over are frictionless and massless, so we don't have to worry about their effects. You can just imagine that the two ropes are just connected together. Okie dokie. Let's see here. What is the first thing we're going to do to solve a problem? Well, usually the first thing I'm gonna do is draw a picture. We already have a picture in the problem itself, but the next best thing is we're going to draw free body diagrams. So I'm going to draw a free body diagram here for mass 1 and over here for mass 2. So for mass 1, I have a force normal. It's normal to the surface. I have a tension upward, force tension, and I have gravity downward, force gravity. Meanwhile, for the other cart, well, this guy has force m1g. This one is going to have force gravity 2, meaning the force gravity on cart number 2 is naturally m2g. Tension force for it is Ft. I'm going to just recycle the name Ft because turns out these two tension forces are on the same rope, and because the pulley is frictionless, these two tension forces are the same. So that's one of the critical things to recognize when you're solving this sort of problem, is that the tension force here and the tension force there are the same. So these two tensions are the same magnitude. They're different directions, but the same magnitude. And then finally, force normal. Okie dokie. I think that's all the forces. There are no friction. If there were friction, we'd have to add friction to this, but there is no friction, so that's that. Okie dokie. So this thing is going to accelerate. And I'm going to draw the acceleration in red. This cart is going to accelerate that direction, and naturally this cart is going to accelerate that direction. They're going to have the same acceleration. They're connected together by a rope. If one moves, the other moves. So they have the same magnitude of their acceleration. The direction is different, but I'm just going to worry about the magnitude. And since the magnitude is the same for both of them, I'm just going to call that magnitude A, whether it applies to 1 or 2. Okay, so now I can do the sum of forces on the various objects. When I do the sum of forces on each one, I can do the sum of forces in the x direction, sum of forces in the y direction. Now I'm going to do a little trick here. For the cart on the angle, I'm going to use a coordinate system which is tipped, and for the cart on the top, I'm going to use a coordinate system which is not tipped. So the way I'll draw that here is I will call up here the x, well, actually, I'll call the x direction the forward direction, x, y up. For this one, I'm going to call x, y that way. Now, that's a little weird. I'm using two coordinate systems in the same problem. It's actually okay the way I'll do it. You can the real rigorous way to think of this is that direction is the x direction. It is referred to with the fancy word is known as a generalized coordinate. It's just the coordinate that measures how far that way the cart has gone. Okay, so we can do the sum of forces in the x direction for mass number 1, and we would get plus mg. Let's see, is it going to be sine or cosine? I want the thing that's pulling it down the hill, because down the hill is positive. So I'm going to break up mg. Let's do another color. Break up mg into two components. That's the angle. So you'll notice that that angle there is the same as that angle there. How do I know that? Well, if you imagine theta going to 0, becomes flat, making that this side goes flat. Both this angle and that angle go to zeros. They're probably the same angle. So you can, looking at this green triangle here, you see that the x component, aka that component, is, let me redraw this with the mg on the other side so you can see this a little better. So I'm going to put m1g over here, and this and that are the two components, where this one is mg sine theta. So we have mg sine theta. Mg sine theta going down the hill, and going back up the hill we have tension. Our acceleration, now I don't draw acceleration as a force in the free body diagram, I draw it off to the side. The acceleration is that direction, down the hill. So if we write the equation F equals ma, we get 1a. So, and I put a 1 here and a 1 here because these are both mass number 1 that we're dealing with. Okay, so this is F equals ma in the x direction for this mass. Oh, we could also do the forces in the y direction, and we would find that mg cosine theta equals normal force. Cool. We weren't asked for it, but whatever. It's a cool thing to know. Now let's turn to cart number 2. We can write F equals ma for cart number 2. So we're going to do that in x direction. If we did F equals ma in the y direction for cart number 2, we'd also find that force normal in this case just equals m2g. Also cool to know, but unnecessary. But if we do it in the x direction, we find there's only one force, tension, and it points in the x direction, causing m2a. Okay, so I have two equations. What are my unknowns? I'm going to underline my unknowns. My unknowns are tension. I don't know tension. And I don't know acceleration. But I have two unknowns, two equations. I can solve this. We could either solve for tension or acceleration, which are the two things we're asked for. So I'm going to do number 1 first. So I'm going to solve for acceleration first, which means I need to eliminate t. So I'm going to plug this t into here and get m1g sine theta. That's an n. Sine theta is minus t, but t is m2a is equal to m1a. Okay, now I'm down to one equation, one unknown, aka a. I want to get a by itself. So m1g sine theta is equal to m1a plus m2a. Okay, let's do this a little more. mg sine theta is equal to m1 plus m2a, divide by m1 plus m2, and we get a is equal to m1g sine theta over m1 plus m2. So that is our first answer. Anytime you get an answer, you want to check some things, especially if it's a complicated answer like this. Let's check units first. So units of mass, kilograms, units of gravity, meters per second squared, kilograms in the bottom, kilograms plus kilograms is still kilograms. The kilograms cancel. We're left with meters per second squared. Sine has no units, so I can just leave it out. So yeah, the n units are meters per second squared. Awesome. That's what it's supposed to be. We're looking for acceleration. Okay. What else can I check? Well, let's check some limits. What happens if theta is 0? Meaning, if theta is 0, the whole thing is flat. You just have two carts connect on a flat plane connected together by a rope. Well, they're not going to go anywhere because there's no downhill to pull them. So if sine of theta, if theta is 0, sine of 0 is 0. So we would get a of 0. That's good. If theta is 0, it shouldn't go anywhere. What else can we have? How about m1 is 0? So if M1 is 0, well, there's nothing pulling M2 down the hill, so M2 won't go anywhere. So if M1 is 0, we get 0 over 0 plus M2, which is 0. That checks out. If M1 is 0, there will be no acceleration. Let's see, what else can we check? How about M2 equals 0? So if M2 equals 0, basically, we just have mass 1 rolling down the hill by itself. M2, you can drop that there. The M1s will cancel, and we'll get g sine theta, which is how fast it would accelerate down the hill by itself. Okay, so that's how you can kind of check the correctness of this answer. In some sense, this is the forward force. M1 g sine theta is the force pushing it forward, and M1 plus M2 is the inertia holding it back. Okay, so that's part one. Let's do part two. Well, to do part two, I can just reuse this equation up here, where I have T is equal to M2A. Sorry, A, not G. A, I can plug in A, and I get T is equal to M2 M1G sine theta over M1 plus M2. You can also check the limits on this. One of the limits that will be different will be if M2 is 0. So if M2 is 0, now the answer is 0. This is because if M2 is 0, there's nothing to pull, so there's no tension. Okay, so that's how you solve this problem. Good luck on the rest of the homework.